one second, how I understand or how I go along developing machine learning potentials. And today's talk will mainly focus on machine learning potentials for complex aqueous systems and how you can kind of easily obtain such models. And just at the beginning, I would like to give you kind of my small overview of machine learning potentials, kind of the machine learning potentials in a nutshell. That should also, of course, summarize some aspects that you have been heard over the last 2 days. And I mean, the main idea is, of course, that we would like to develop a representation of the structure-energy relationship. And usually for essentially all of the existing machine learning potential approaches, that is usually done in a two-step process. So you've seen that in most of the other talks. First of all, our structure is actually transferred into a more mathematical description based on so-called descriptors, which give an idea of the atomic environment around each atom. And that is then inputted or like fed into a machine learning model, which is doing regression in order to output energies and forces. And another central concept that is kind of common to most approaches is this locality approach, where you usually restrict yourself with the descriptors to a certain cutoff around each atom. And you might have also seen some approaches that can actually go beyond that in order to include long-range interactions. But for what I've been talking about, this will always really remain under these locality assumptions. And then really the main job of what we're trying to do is like developing or building a training set that is representative for the kind of process we are interested in. So in order to highlight that, I show here in a completely abstract feature space certain points that have been selected. And the job of the machine learning potential is then to really interpolate between kind of nearest points in order to give you meaningful like prediction of the current point in question, which is shown in red here. So as you already see, the really difficult part about that is actually coming up with like meaningful and representative training data. And I will kind of touch on that, how you can automate this process based on active learning concepts in today's talk. And the kind of machine learning method I'm usually applying is the high-dimensional neural network potential formalism pioneered by Jörg Behler. And the main job of representing the structure-energy relationship, as you have already seen in Long's talk, for example, on Monday, is done by like this two-step procedure of first transforming your coordinates into these input vectors based on so-called atomic-centered symmetry functions, atom-centered symmetry functions. And they have a radial component and an angular component, which gives you kind of an input vector really for each atom. And in the next step, this is fed into so-called atomic neural networks, which then output an atomic energy that sums up to the total energy. And if you are interested in using this kind of formalism, you can either do that in simulations in CV2K or, for example, in LEMS, both with open source implementations. However, if you now really start thinking about like really building such a model, you have to really, you directly arrive at the task of constructing your training set. And kind of the naive approach to go along there, this process is you might simply sample your potential energy surface with the reference method that you are interested in representing, and you just pick random points from this sampled potential energy surface. For example, shown here on the right by these black dots that I have kind of drawn from the trajectory. And then you would maybe just train your model. But the questions that should immediately pop up are if you really are able to select the best points by such a random approach, or if the models that you train, if you can really trust them, because you just get what you do, and you have no real estimate how good your prediction is. And in order to highlight that, I show here on the right just 8 different outcomes of 8 different training processes for neural network potentials, and you immediately see that kind of all of them will be able to kind of represent the potential energy surface there, but with variable quality. And I mean, usually then in a naive way, choose simply the best out of the 8 models that you have trained and stick with that. However, you still don't really know if this is like really the best in total, and you don't have any control of your errors in the end, because you only get your prediction. And what is actually much more elegant to do is to not throw away all these fits that you have done, but rather combine them into a so-called committee model. And the idea there is that instead of a single prediction, you get multiple predictions that you can average over in order to get a new, more accurate prediction. And in addition, this is usually also a bit more robust because you are kind of counterbalancing fluctuations in these models. And another nice aspect of that approach is that you also at the same time have access to the variance of your prediction, which can be used as an error estimate of the model. And so this is shown here on the right, where the blue line would be the prediction of the average, and the gray area is then the standard deviation of the prediction. And you can kind of see that there might be some regions with higher error compared to other regions. And that is actually a very useful tool because it allows you to really select regions in configuration space where your model is kind of uncertain in its prediction. And that gives rise to a very powerful active learning procedure called query by committee, in which you can kind of selectively improve your training set. For example, in this region, we have seen relatively high errors. So we can really put a new training point into our training data, training set, and refit our model, and then improve the error and also the prediction in this region. And you can do that multiple times and really iteratively improve your model, which gives rise to a very powerful like data generation algorithm. And just to recap, why committees are actually kind of useful and maybe advantageous over normal models. Like what I've showed you is that they are actually usually leading to a more accurate prediction. And at the same time, you have this estimate of the uncertainty. Another side effect is that you're actually usually reducing overfitting issues, and you have access to this very nice active learning procedure that can really like build up your training set. And you might be now wondering, like instead of a single model, we now have 8 or even more models. Shouldn't there be a larger computational overhead? However, in practice, you can actually realize that you can formulate these committees in such a way that you simply share the first bit of the transformation of the atomic structure based on these descriptors within your committee, and then only the last bit, the actual machine learning regression, is different in all these committees. And that actually leads to the fact, or to a situation where you are not really paying more because the descriptors are actually what is the computational bottleneck. So in the end, this whole committee procedure is not really more expensive, only like slightly more expensive than running a single model. And at the same time, you get an error estimate and can build up your training set based on this active learning procedure. So how can this now be used in order to really generate like a simple or easy framework in order to tackle complex systems? And so in our work, in our recent work, we have come up with kind of an end-to-end framework where you would be interested in a certain system and then just generate a model that can really tackle the questions you want to answer. And the conceptual idea behind all this is that we make the job a little bit easier by concentrating on a specific thermodynamic condition, so a given temperature and pressure. And then the main task is really to remove as much user input as possible and automate most of the development steps. In the end, it's also very important to have kind of an automated validation scheme in order to build trust in the model that you have developed. And just a side note, all this development that I'm presenting is open source development, which you can simply use for your own work if you want. And how does that machine learning framework look like that we came up with. It mainly concentrates on just a single ab initio trajectory as an input, which can be relatively small scale and short, which means like 30 picoseconds, and small in that respect means it must have still all the environments that are kind of necessary for the system you're interested in. Can't make it too small. And then the active learning framework that we have developed really builds on the concept of this query by committee procedure, where we would iteratively like train our committee neural network model and then kind of filter the ab initio trajectory in order to select points with highest error estimates to build up our training set. And that usually converges relatively fast. We can then generate a final machine learning potential and apply that to larger system sizes and longer simulation times. If you're now wondering for what kind of systems we have tested that, so this is all aqueous systems that are like reasonably complex. We have looked at ions in solution, we've looked at water nanotubes, different types of nanotubes, carbon or HBN nanotubes, water confined by MOS2 sheets, and water on the titanium dioxide surface. And with this procedure that I've just presented in the previous slide, where we really just run a single ab initio trajectory for these systems and then build our machine learning model on top of that, we have developed 6 models for all these systems. And the final training set usually comprised only roughly 300 structures for each of these systems. However, now you kind of arrive at the next problem. Sure, you have developed 6 models, but how do you know that they are actually meaningful? So this brings me to the next point, the validation of this. So we have spent some time thinking about meaningful measures of the accuracy of the model beyond just simple RMSE values. And we have kind of identified these 3 main components which can be evaluated for essentially all the systems you're interested in. We have a structured property, a dynamical property, and more like a machine learning property. And the structured property is the radial distribution function. For example, shown here for this fluoride water system, comparing the neural network prediction and the DFT reference, which gives you an idea of how the structure is really represented. Thermodynamical properties are represented by the model. And then secondly, we look at the dynamical property, which is the vibrational density of states, again shown here, resolved for all the elements in the system of the fluoride water setup. And we also use that in order to benchmark all our models. And the last final thing is looking at the force root mean square error, which is kind of giving you an idea of like how the most important part for an MD simulation would be represented. And like in this automated validation procedure, we evaluate all these properties for the different systems and reduce the final performance into a single score for all these 3 properties by suitable distance measurements. And this gives you a relatively handy or like shortened like summary of the accuracy of the model, which I show here on the right for the different systems for the 6 setups. And first of all, you will notice that all of these scores are rather high, so all like 90% roughly or above. And between the different models, we do not really see large differences. So that means the kind of accuracy that I've shown in the previous slide here for the fluoride water setup is kind of maintained for all these other complex aqueous systems. And at the same time, we might see that the radial distribution functions, so the structural properties, kind of giving the highest score here, whereas the forces give the lowest one. But the main summary of this is that like all of these various properties are actually represented with relatively high accuracy compared to the DFT reference. And in order to really convince ourselves that this is meaningful for other properties as well, we have actually checked other things like hydrogen bonding, the density profiles, the water orientation, and overall saw very good agreement with our reference. So this now means that essentially for all these diverse systems, for all the 6 systems, we could look in detail in long simulations with extended system sizes and try to answer chemical questions. And in order to highlight that, I will now concentrate on the titanium dioxide system that we have studied. And I mean, the original ab initio trajectory there has just been 30 picoseconds for roughly 400 atoms, relatively short, whereas our committee neural network model can reach much longer simulation times on the order of many nanoseconds, while at the same time extending the system size by a factor of 4. And the side note here is that these simulations are really, really fast, so a factor of like 4 to 5 orders of magnitude faster, which really allows you to converge whatever properties you are interested in. And kind of insight that you could gain into these systems is shown here in this slide. So on top, you again see kind of a side snapshot of the setup. We then have looked at the density profile, which you can also just get from your ab initio MD, but you already see that this is relatively noisy in the short ab initio MD, whereas we can really converge it with the neural network potential. And then you can also actually look at other properties that are inaccessible by the very short ab initio MD. For example, the layer or distance resolved diffusion constant, both in the parallel and perpendicular direction with respect to the surface. And this is not possible with the limited statistics of the ab initio MD. And another nice aspect is during the whole simulation, you actually have access to the committee disagreement, which can then really be used, for example, to resolve your error, the predicted error of the model as the function of the height, or also over the whole trajectory, which can be used in order to build trust in the simulations you are running. And another aspect, for example, would be the free energy profile of water absorbing on the surface, which can't be converged at all with the short ab initio MD, but can be nicely resolved with the longer simulations. And another example for what you can use this approach would be, for example, just liquid water itself. So this is showing you now work that is based on a hybrid DFT functional. And at the starting point, we have simply taken a 300 Kelvin ab initio MD and then have started this active learning procedure in order to build the training set. And this concentrates a bit more on how the usual active learning procedure looks like. So in each of these active learning iterations, we add 20 new points to our training set. And the top plot here actually shows you the committee disagreement for the different sets of structures we have. So there's first of all the training set. Then there's this large pool of candidate structures. And then there's the selected structures, which actually have the highest predicted error. And you see that in the course of the active learning procedure, this is actually decaying really, really fast to a very, very small committee disagreements, where you actually do not have much more higher errors in the candidate structures, which you could pick out. So this kind of signals that you are converging your active learning. And at the same time, you can also look at the real performance of the model for a completely independent validation set. And you will also see that in there, you are converging really fast with the number of structures that you select, because you are able to really pick out the outliers that are difficult to represent with your model. And this graph also shows the performance for the differently sized committees. And there you can actually see that using the committee prediction enhances your predictive power quite a bit, and you gain accuracy overall. And for what can you then use this model that has been trained on 100 points? So you can actually start using it for enhanced temperatures or larger temperatures, apply it to different phases. And a very nice aspect of the whole procedure is that you will always have access to your disagreement during these simulations, which then are able to highlight regions of uncertainty. And in order to show you that, I have here a snapshot of the water-air interface where I color code every atom based on the committee disagreement. And you nicely see that the actual interface, the interface water molecules are much harder to represent by this model that has been trained only on bulk configurations, so which is very much expected. It should not be able to give you a good prediction in this region. And this actually can also be used for another nice concept, you can actually realize that the small disagreement is kind of related to stable and an accurate model. And then you can think about defining a biasing potential, which acts on this, oops, sorry, I'm jumping too much, acts on this disagreement. So you kind of impose a barrier around the region of your training set, which is well known, where you have a low disagreement, and prevent your simulations to enter the regions with high disagreement. That can be done quite easily, and it's actually in the end a relatively mild bias, which kind of stabilizes your dynamics or your simulation. And that can be used, for example, in cases where you are in an exploratory phase and want to kind of get an idea of other situations and in order to generate new structures. And so this can then be all combined into kind of an adaptive workflow shown here, where you start at a given thermodynamic point and then expand into different regions of phase space using all these concepts of active learning in order to build up your training set. And the nice aspect of that is you're using like the previous generation model for the structure generation, which then saves you a lot of computational time, because you will really only have to evaluate the expensive DFT reference for those few points that you select to be important for your training set. And for like just a final note on this, we have of course also benchmarked the performance of this. You see again very good agreement, for example, for melting, for the melting point, the density, radial distribution functions, IR spectrum, and so on, and also for example, for the vibrational density of states shown here on the right. And that can then be used, for example, to study the phase diagram of just a single layer of water confined by a Leonard-Jones potential, which is recent work in collaboration with Venkat Kapil. And we like using this machine learning approach, we are able to kind of get a full picture of the phase diagram here. The nice aspect of that is that we, like, I will not go into details here, but we actually see some new previously not seen phases, a so-called hexatic phase, which is neither a liquid or nor a solid. So kind of phase in between those two, and we recover superionic behavior beyond 4 gigapascal and 400 Kelvin, where we essentially have fixed oxygen atoms and then diffusing protons. And I mean, the nice aspect to what this should show you is you're really able to go from just the bulk system at 300 Kelvin to a region that is completely different, which is monolayer water under confinement. And you are at the same time also able to describe reactions as proton transfer with these kind of methods. All right, and that kind of brings me already to the conclusion and the summary. So during this talk, I've shown you how you can kind of simplify the development process of machine learning potentials based on these active learning concepts to end up with a relatively accurate and efficient description of your potential energy surface. And the whole thing is kind of a data-driven and automated generation, which means you don't have to spend that much work yourself. You can let the computer work. And a side note here is that all this is open source development, including the tutorial that I will now switch to, which can be accessed, for example, at this GitHub or from this GitHub repository. And with that, I'm coming to the acknowledgement of my collaborators from the group of Angelos Michaelides mainly, but also from Imperial Eric Müller and from the Charles University Andrei Masamek. And with that, I would stop now for a first round of questions. So let's see, I'm just going to open the chat. There has been a question apparently. Okay. So first of all, are there any questions that are directly like from people? Doesn't look like that. Then I needed.
Oh, sorry. Luigi is raising his hand.
Yeah. Thank you for a very nice talk. I actually had a couple of questions. Well, first a small thing, which is I didn't get when you were talking about the biasing potential based on the disagreement of the predictions, whether you were using it to sample new configurations or to prevent the system from going into, let's say, unstable regions.
Yeah, you can do both. So let's say you have trained a model in a given part of the phase space and would like to expand it to a different one. In order to, and then by doing that, you realize the simulation is actually not stable at the beginning when you do that. So then you can try applying this biasing potential in order to make it stable and still generate new structures. So this would kind of be the normal application of that.
Okay, thanks. And but do you use? I mean, so you're using? I mean, the disagreement as a, let's say, as a way to quantify the extrapolation.
Yeah,
so do you put? So I remember from some of the previous talk that they were saying about, okay, you need a multiple threshold scheme because you don't want to include every, I mean, very unphysically stable. So do you do something like that? Or
yeah, I mean, this is essentially leading to like the biasing. You can shift it to a given disagreement level. So you can still allow for kind of intermediate disagreements, which are the ones you want to include in your training set, and prevent these extreme cases of your system blowing up. And I mean, you could actually think about extending that into something like enhanced sampling for intermediate disagreements, really. But like we haven't done that in the work, in our work currently.
No, thank you very much.
Definitely true. You want to prevent these extreme situations where your system explodes. So those need to be prevented, and that's kind of what the bias can do.
And if I may, another, I mean, it's more, actually, it's more asking for a comment than a question. So, also here you're saying, I mean, small disagreement is equal to stable and accurate model. I mean, the problem with neural network, I would say, I mean, this is a, let's say, is a necessary, but it's not granted that it's a sufficient condition. I mean, it's a condition, because they might also be that all of your models are doing it the wrong and the same way.
Yeah.
So, for instance, I mean,
No, this is definitely
so it's
what you are not able to really get from the committee disagreement is kind of the bias of the model. But you can use the committee disagreement like by looking at the expansion of your training data in order to estimate the bias of your model, because at some point your committee disagreement is essentially zero under infinite data. And that would, like, the remaining force or error, energy error would then be the bias of the underlying function form you are using. But definitely the bias is still there, right? This you can't get rid of that.
Thank you.
Are there other questions? Otherwise, I'm going to quickly read this comment here. Ensemble neural network uncertainties are known to be overconfident at out of training distribution errors. Have you done some analysis on reliability of NN uncertainties, let's say with respect to Bayesian methods such as no? We haven't done that yet, no. I mean, we have looked more at the qualitative level of how the errors can be used in order to give you an idea of the accuracy of your model. And I mean, in general, yes, that is definitely true. Out of sample points are you get into trouble with an accurate prediction of the error based on the committee disagreement. But I would still say that just having an error estimate that goes in the kind of right direction is already quite useful. So, but of course, you can do more quantitative analysis in order to improve this. I hope that kind of answers this question.
Thank you.
Edgar's raised his hand as well.
Yes, hi, thank you. I guess I was going to add to that.
I think what I'm going to be talking about in a moment is a similar application in the sense that you're considering applying these models for a specific state point and actually interpolating within the space of configurations that you've sampled with your training, right? So you're kind of by design avoiding terrible out of sample predictions and terrible extrapolation just by sticking to a particular state point.
Yeah, definitely.
Just as a comment, I think I'll basically suggest a similar strategy, and I think it'll profit from the same kind of limited application scenario.
I mean, maybe a final comment on this, because it seems to raise a lot of questions. I don't really would apply this for your final production runs, this biasing of the committee disagreement, but it's rather a tool that you can use in order to explore new phases that you haven't yet included in your model. And I totally agree with your statement.
Can I ask you? I think you said something quickly about this, and I didn't quite catch it. But you've also considered basically applying an opposite bias, the inverse bias, and driving the system into the uncertain regions, right, to motivate sampling, kind of expanding the limits of your training data.
Yeah, but we never really ended up doing it yet. Of course, it could be done, right? It's kind of the next step once you realize that you want kind of intermediate disagreement. You could think about.
I suppose it would be at the price of simulations blowing up very quickly and then having to be restarted upon retraining, right? I guess you'd very quickly end up with completely non-physical configurations that you have to worry about this. Yeah. Okay, thank you.
I can't see another raised hand at the moment, so would then probably switch to the tutorial, if that's fine.
Yeah, I think go ahead.
All right.
I don't see any questions either.
So first of all, small comment. Unfortunately, DeepNote made some trouble yesterday when we were when I was trying to extend the tutorial a bit, and so I think I'm not 100% sure if the current DeepNote model is actually working. So maybe one of the organizers could quickly give me a statement on that.
Sorry, yeah, I don't know.
Okay, then we will just assume that this will be sorted out hopefully soon or in the future, and then you will have access also to a DeepNote tutorial. But for the moment being, I will simply guide you through the tutorial I prepared in my terminal, and I hope you can see my terminal now. That should be fine. And I mean, the tutorial basically walks you through these individual steps of the active learning framework that we have come up with, where you first of all would generate an ab initio trajectory, then filter that in order to generate a training set based on active learning, and then finally apply your model for extended simulations. And also the validation is shown here. So the first step is simply the ab initio MD, and for this tutorial, this is a rather simple setup. So it is actually just this Sundel cation, which is two waters with a shared proton in the middle in the gas phase, in order to make something that is rather fast. And for the electronic structure itself, I decided to use just DFTB, which is not that accurate, but still can be considered ab initio. And so the setup that we have here is now just as a showcase 5,000 steps of the Sundel cation at 300 Kelvin, giving this DFTB settings. And I mean, you can in principle just run that with CP2K, which will then generate a trajectory relatively fast, as you see here, which you can then in the next step use for this active learning setup. So we'll just wait a bit until that finishes. This is just 5,000 steps, should be rather fast. And I can already start moving to the next directory, which is then using this Python package that we have developed for the active learning. And side note on that, so what it basically does is it reads in the CP2K output, including the positions and forces and energies, which are then really used in order to build up your training set. And so the first bit in this Python script would be just dealing with reading the structures. And then the second bit is actually on the specification of the machine learning potential, where the first bit would be the settings that you feed into the neural network, N2P2 constructor. So N2P2 is the fitting code we are usually using. The main important parameters here are the size of the committee, which is n, and then kind of the number of cores and number of tasks you want to put into your training. And then the actual query by committee is controlled by the second settings function, where you have first of all just the initial training set, which is consistent of 20 random structures, and then in each iteration you add 10 new structures to your training set. The optimization of your neural network potentials is done relatively loose in this active learning procedure in order to improve efficiency. This is still fine because you are not really applying these models for any simulations. You are rather just after a quick estimate of your errors to filter out new structures. So this number of epochs, which controls kind of the convergence of the individual neural networks, can be relatively small. And then overall, we do 15 of these active learning iterations and query 500 random points in each of these iterations. And that can be easily extended in principle to the full trajectory length. So in order to make that work, you see the CP2K run has now also finished. We simply call Python. And this should also be now reasonably fast. What happens here now is, as I said, the structures are read in, and then the actual query by committee loop starts, which then first of all performs the training of the committee. Afterwards, you extract random structures from your ab initio trajectory and predict the energy of those and forces of those with the committee in order to select new structures. And this has been done now reasonably fast for this setup in 3 seconds, and it reports 3 key properties here: the estimate of the force error for the training set, then the error for the candidates, which is the larger pool of structures, and then the error for those samples that have actually been selected to be included in your training set. And you see that in the course of this active learning procedure, all of them are actually decreasing quite a bit, where usually your selected points have the highest error, but after some time, you actually kind of converge to a situation where you are essentially at the same error for the selected points and your training data. So this signals then that your active learning procedure is converging. And let's have a look. So it's currently at iteration 11. At the same time, you actually also see that by really picking out the outliers, those cases that are hard to represent for the model, your training error becomes larger than the actual candidate structures from the ab initio trajectory. So you really pick out the most representative points that are important for improving your predictive power of the model. And at the same time, sometimes you might see that some substructures have already been selected in a previous iteration, and those are not again added to the training set. So, and this is now almost at its end. It's the last iteration. I just have a quick look in the chat. Okay. So if anyone has any questions on what I'm currently doing, please just interrupt me in order to guide you through what I'm trying to do here. And now the output of that is actually a separate directory for each of these active learning iterations, where you would be where you could find more detailed information of how the active learning worked. But instead, we just now go to the next step, where we will create the final model. which is necessary because I just explained that during the active learning, we can get away by doing a very loose optimization of our machine learning potentials. But for the final application, you actually want a more stringent one that is better converged. And so this needs to be done kind of in a separate step afterwards. So and that can be just done again by calling this Python script. And this will now take a bit longer than the previous trainings of these individual models because we actually do a more stringent optimization. Let's see.
There's a question from Daniel Musota about what electronic structure codes are compatible with AML.
Yeah, so far we have only really used CP2K, but it's all, at least all consistent in that respect that you can run the up initial trajectory or also the neural network potential simulations with that. But it is relatively straightforward to implement new I/O routines for other electronic structure code if that is needed, really. But we haven't done it yet. We have concentrated only on CP2K. All right, so the final training is done now. So that means we could now move on to the actual simulation using this method, this new developed model. So that can be done here now. And again, this will run reasonably fast, as we see here. Actually, comparing timing here is a bit difficult because the DFTB setup is already really cheap, but you're still gaining roughly an order of magnitude compared to the DFTB setup. So this will just continue to run and produce like more structures, and in principle it can be used to significantly extend the length of your previous up initial trajectory.
There's also a question from Chanbun asking about the differences between steps 2 and 3.
Yeah, okay, so again, number 2 was really building your training set, which where you can kind of get away with looser optimization of your neural network potentials. Whereas the step number 3 is really this stringent optimization of the final training data that you have in order to produce the final model. Hope that's a bit clearer. And that brings me kind of to the last step, which we can also just execute now already, which is the scoring of the the validation of the developed model, which would then look at your initial trajectory and compare the kind of neural network potential trajectory to that for these 3 key properties that I have mentioned in the talk. So the radial distribution function, which is the first one done here, and then second, the bidirectional density of states, and third, the prediction of the forces. So if we run that now, this will kind of take the up initial trajectory and the neural network potential trajectory and compare them, and it outputs kind of this summary of the accuracy for the various like radial distribution functions, and here bidirectional density of states, as well as for the different force components in the system. And you can see also for this completely different setup system in the gas phase, we again end up with relatively similar values compared to those reported for the more complex aqueous systems I had presented during my talk. So, and what you also get is actually like individual PDFs or plots for the different radial distribution functions, for example. So we can have a direct look at how the model is doing. And of course, radial distribution function is probably not the most suitable for a gas phase system, but it can still give you kind of a summary of how structural properties are presented by the model. And you see that we essentially have very good agreement between the DFTB and NMP prediction. And similarly, that can also be seen, for example, for the vibration density of states of the hydrogen atom. So here. Although, of course, this is also a bit impacted by statistics. So you should keep in mind that some variation in that is also due to, for example, the limited statistics you have provided based on the ab initio end. All right, and if you actually want to take the like the actual data of these underlying scores and plot them yourself, you get an output of a pickle file which can be loaded with Python and then plotted as you like, basically. So this would be kind of the full from ab initio trajectory to model tutorial, including a validation in this example. And with that, I would kind of be at the end of the tutorial and looking forward to any kind of questions that you might still have.
Thank you, Christoph. I think Edgar has been raising his hand.
Yes, I've got another question. So in the active learning procedure, you're iteratively rebuilding committees of neural network models. And I was wondering whether you somehow employ, say, a transfer learning strategy or something to render this a bit cheaper and maybe have a more continuous evolution of the potential energy surface that you produce as you increase the number of training data. So I suppose you could either start from the neural network weights and that you had previously computed, or maybe do something like the implanting that Berg was talking about earlier this week. Is there anything along the lines in the works already implemented?
We actually didn't really recycle any of the information that was learned during in the neural networks during the active learning procedure. We rather try to make it as cheap as possible by kind of starting all these individual active learning sessions kind of from scratch. So we actually also don't have like a single training set that is extended all the time, but we rather kind of develop the most suitable one for all the different conditions we are interested in.
This makes a whole lot of sense for me, but I suppose you still have, I don't know, some non-zero number of active learning iterations, active learning steps where you, as you put it, I suppose, retrain neural networks from scratch. I was wondering whether there might be a benefit to kind of reusing whatever you've basically got.
There could be definitely, but
learning step maybe.
Yeah, no, sorry, but I think in practice, I wouldn't see that as the bottleneck of this approach. So usually, even for the complex systems, we like I have highlighted here, right? We usually could run the actual generation of the model essentially overnight. So of course on a cluster, it's not done on like a normal laptop, but all that is rather fast to do. So I don't think this is the current bottleneck. I would rather say that the ab initio trajectory is still the most expensive.
That makes sense.
Yeah.
Thank you.
But yeah, all right.
There's a question from Mari as well.
Yes, thank you so much for a very informative talk. I had a question about this model for water in complex environments. Do you need to worry about the complex environments in your descriptors, or yeah? Yeah,
so this is something I have kind of not mentioned at all. So the type of descriptors we apply here are just the normal Bela-Parinello type symmetry functions, and we actually use a completely general set of descriptors that we apply to all of these systems. And in this active learning package, this is generated kind of automatically for you. And I mean, those might not be the perfect descriptors for all the systems that there are, but due to the active learning and the added stability of the committee, we haven't seen like huge disadvantages of choosing a completely general set of descriptors. So This is kind of my take on that. But I'm definitely not claiming that this is already the perfect thing. It just kind of works well enough for the kind of systems we are interested in, so that we don't have to like develop a more sophisticated set.
I see. Okay, thank you.
And there's a question in the chat from Oliver Morrison. He's asking in practice whether you perform all of these steps in just in one script.
In practice, what do you mean exactly with that? I mean, usually I definitely see, for example, the ab initio trajectory as a separate thing, because that is a bit uncoupled. That can run on a huge, huge HPC resources. But once you have that, I would usually then start this query by committee job that would be again a separate step. Afterwards, once you have kind of generated your training data, get the final model, and then you can do whatever you want with this final model. You can apply it for larger simulations, longer simulations, and in principle also do some temperature variations. So these models that we usually generated are also able to do a bit of like temperature scans without losing their predictive power. But I still see that like all of these are essentially separate steps. They could be combined in a completely automated procedure, but usually in practice they are separate.
Mm-hmm. Yeah, I guess you want to jump in and kind of explore a bit and decide what the next best step would be.
In order to further improve this, you mean? Or
yeah, I mean, in between all these separate steps, I guess there's, yeah, I'm wondering if there's some, like, depending on the output of one step, you would be whether you would be deciding what to do next slightly.
Yeah, I think you can definitely think about just combining what we have here already in some kind of automated AIDA protocol, which would then be applied to whatever system you have in mind. But of course, that needs a bit of care on like really checking individual things, because when something goes wrong, you usually still have to spend a bit of time. So that would be kind of what I would be a bit worried if you simply apply it as a complete black box.
Yeah, absolutely. Any final questions for Christoph? If not, thank you very much. Yeah, thank you very much for the talk, Christoph. And I think the next talk is Edgar's in 10 minutes. Thank you.